Okay, hi everyone. So now we will talk about the first translation theorem. So this is the following. So suppose you have a function f and you times it an exponential for some a, um, a, and you want to find its Laplace transform. Then you have the following. So this says e to the minus st, e t of t. Right, and then so you group these two together. And this is nothing else but the Laplace transform of the function f of t. But now you shifted s. Okay, so that's it. And now let's do some applications. Solve the initial value problem, y double prime, 4y prime, 4y equal to the polynomial t to the 3 and then times exponential. And you need two initial data, right? So you need one for the solution itself and its derivative, because you have second order. Okay, so let's use the Laplace method to solve it. You can also solve this with the method of undetermined coefficients. So either way is fine, but Laplace is faster. Okay, so recall the following. So if you have the following ODE, so AY, CY, PY equal to GT, then you have the following. Y is equal to the Laplace inverse of s squared plus as plus b, Laplace transform of g plus a plus s initial data at 0, and y prime at 0. Okay, you can do this yourself just by taking Laplace transform of both sides, LT of both sides. All right. Right, so we just plug in what we have. So Laplace inverse s squared plus 4s plus 4, Laplace transform of t cubed e to the minus 2t. And then, right, and the other two are 4 plus s times 0 plus 0. Okay. So let's use our shift formula. So find Lt cubed e to the minus 2t. So by the shift, so first translation theorem, this is, so let me put s. Right, t to the 3, and then s minus minus 2. Okay. Recall that the Laplace transform of a polynomial is equal to n factorial over s to the n plus 1. So you can find it in the table, and you can use that directly. Okay, so that means the following. So n is 3, and you have 3 factorial, and then s plus 2 to the 3 plus 1. Okay, so that's how we use the translation theorem. Okay, so now let's return to star. So we have the following. We have Laplace inverse. Let's factor the denominator. So it's s plus 2 to the 2. And then on top, we have 3 factorial over s plus 2 to the 4. So we're asking the Laplace inverse of s plus 2 to the 4. Okay. So again, we use the formula L to the n is n factorial Sn plus 1, but we use it for 6. So n would be 5. So we divide and multiply by 5. So let me write it. So 5 factorial over s plus 2 to the 5 plus 1. Right, so we'll use let me write it this way to make it more clear. So t to the n is equal to Laplace inverse of this. So we get t to the 5. Right, but there's also a shift. Yes, so let me write it this way. So this is, let me write it this way. So this is 5 factorial s. It's fine. Let me just write. So we have t to the 5 times e to the minus 2t. Right? So we use the shift formula from above. This is because we have s plus 2 here. So let me make it clear. Here. So we're using the general formula L to the Tn e to the minus at is equal to L to the Tn s minus a. So we're doing that same thing here. Okay. So here we use L inverse, L of t to the 5 s minus minus 2. All right. Okay. So that was the solution. So yt is equal to 5 times 4, 20, t to the 5 e to the minus 2t. All right, let's do one more example. Solve the IVP y double prime y prime y over 2 equal to 1, given that y0 is 0 and y prime is also 0. We use our formula, so y of t is equal to Laplace inverse of s squared plus s plus 1/2, and then on top we have L of 1, okay, and the other two are 0. So you can do that direct, just use the formula from here. So let me call it star. Okay. All right. So the tricky part for this is that this guy has only complex roots. So let me do that. Right. So okay. So first L of 1. This is t to the 0. So it's just 1 over s. So that's easy. That's that. And then we have to factor s squared plus s plus a half. The roots are as follows: s minus a half minus a half I, and s plus, sorry, s a half, but then plus. In other words, if you don't like complex roots, you can write it as s plus a half squared plus 1/4. So either way is fine. It's up to you. Okay, so coming back, we have L inverse s plus a half squared plus 1 over 4, and then 1 over s on top. But now we want to split this, so we do partial fractions. Partial fractions. We just call it PF from now on. So we have the following: we have 1 over s and we're looking for some number a and some numbers b and c. So if you do the calculations, you will get a is equal to 2, and then s plus bc is equal to minus 2s minus 2. Okay. All right. So we have y is equal to Laplace inverse of 2 over s, and then plus minus 2 minus 2s minus 2, and then this factor. Okay, so let's use our translation theorem for this guy. So recall Laplace of cosine kt. So again, you can use the table for this. It's s and s squared plus k squared. And Laplace transform of sine kt is k over s squared plus k squared. Okay. And so if you do translations, so by first translation theorem, we have the following. This guy is fine. So this guy returns to constant. So 2 times 1. But now we have to split this guy. So minus 2 times s over s plus a half, and minus 2 Laplace inverse of, so I need 1 over 2. And I multiply by it. So we did this because this is k, right? And this is k squared. All right. So now let's use our translation theorem. So this is still 2. And now we have Laplace inverse of cosine 1 over 4. 1 over 2, sorry. With s minus a half. Minus 4 Laplace inverse of the Laplace inverse. So Laplace inverse of the Laplace of now sine a half t, and then same s minus a half. Okay. Now Laplace inverse cancels out with this. Actually, let me use the translation theorem first. So 2 times minus 2 is e to the minus t a half. Okay, almost there. And these two cancel out. Okay. All right. Thank you. So that's it for the first translation theorem.